This is a kite. It originated from the lands of what we now call China over 1,500 years ago. Kite is humanity's first aircraft to practically demonstrate flight and lift. It laid the conceptual groundwork for flight and aerodynamics. Many years later, these simple inventions have taken a colossal form. The modern aircraft. Immense, precise, and incredibly intelligent. They are the backbone of modern transportation and warfare. Consider the Antonov AN-225, a giant among giants. It is the largest cargo aircraft ever built. At nearly 276 feet in length, with wings stretching approximately 290 feet, it dwarfs anything the earliest pioneers could have ever envisioned. The journey from ancient Chinese kites to intelligent fighter jets and immense cargo planes was made possible due to the never-ending experiments of engineers to continually improve a fundamental feature of every airplane, the wings. During the research, German engineers and aircraft designers discovered a type of an airplane wing concept that has never been seen in the aviation industry. This was around 1944. Though conceived, this concept was not implemented until a few years later. This concept is known as the oblique-wing concept or a slewed wing. In the United States, aeronautical engineer Robert Jones, working at the NASA Ames Research Center, revived the concept of the oblique wing in the 1950s. Jones conducted wind tunnel studies and analytical research indicating that a transport-sized oblique-wing aircraft flying at speeds up to Mach 1.4 or 1.4 times the speed of sound could achieve better aerodynamic performance compared to an aircraft with a conventional wing design. Commercial jet airliners with traditional wing designs typically cruise at speeds between 480 and 560 miles per hour at an altitude of around 40,000 feet. These speeds are chosen carefully, striking a balance between fuel efficiency, engine performance, passenger comfort, and operational cost. The oblique wing is a distinctive aircraft design where the wing pivots around the fuselage, allowing one tip to sweep forward and the other backward. This configuration aims to optimize aerodynamic efficiency across a range of speeds, combining the benefits of straight and swept wings. At lower speeds, the wing can be perpendicular to the fuselage, providing maximum lift and control. As speed increases, the wing can pivot to a more swept position, reducing drag and improving fuel efficiency. In aerodynamics, this is a proven theory which drastically reduces drag during flight. According to Robert Jones, implementation of the oblique wing concept means commercial jet airliners could fly a lot faster and efficiently within the next few years. Building upon Jones's research, NASA initiated the development of an experimental aircraft to test the oblique wing concept. In the late 1970s, NASA developed the AD-1, a small pilot-controlled research aircraft, to test the oblique wing concept in flight. The AD-1 conducted 79 flights between 1979 and 1982, gradually increasing wing sweep from 0 to 60 degrees. The test flights provided valuable data on the handling and aerodynamic performance of the oblique wing configuration. The report presented several advantages and disadvantages as well. Now, for an airplane to take flight, it needs to follow certain principles of aerodynamics. Aerodynamics is the study of the behavior of air or any gas as it flows around objects. In aviation, it focuses on how air interacts with aircraft surfaces, particularly the wings, fuselage, and control surfaces. The wings of a conventional airplane is designed in a specific shape known as the airfoil shape. An airfoil is the cross-section of a wing. It is a streamlined shape with a curved upper surface and a flatter lower surface. This distinct shape is designed to manipulate airflow around the wing, which results in lift. Lift is the force essential for overcoming gravity or a body's own weight. It allows an aircraft to stay airborne. A typical airfoil has a leading edge, which is the front edge that first contacts the airflow. There is also the trailing edge, the rear edge of the airfoil, and the chord line. a straight line connecting the leading and trailing edges. There is also the camber, the curvature of the airfoil, upper or lower surfaces. The airfoil also has thickness, the maximum distance between the upper and lower surfaces. The science behind the airfoil's lift generation is associated to Bernoulli's principle. It states that as the speed of a fluid such as air increases, its pressure decreases. Air is a fluid medium, but less denser than its liquid counterparts. The camber or curved upper surface of the airfoil causes the air above it to travel faster than that of the lower surface. This creates lower pressure on the top and higher pressure on the bottom. The pressure difference is what generates lift. However, lift depends on the speed of the airflow over the wings. This is why airplanes speed on the runway before generating lift. The angle at which the wing meets the oncoming airflow is a critical factor. This is known as the angle of attack. As angle of attack increases, lift increases up to a point. Beyond a critical angle of attack, airflow separation occurs, causing a rapid loss of lift known as a stall. Modern aircraft may have variable geometry wings or movable surfaces, such as flaps and slats. This type of airfoil shape is known as a variable camber airfoil. They change the airfoil shape in flight and optimize performance across different speeds and conditions. When the moving air hits the wing, it encounters centripetal force or acceleration. This is the force experienced by passengers when a car makes a sharp turn. The science of aerodynamics involves four main forces: lift, which is the upward force that allows an aircraft to take flight; gravity or weight, the downward force due to the mass of the airplane; thrust, the forward force that propels the airplane, typically generated by the engines; and drag, the resistance that air exerts against the aircraft as it moves forward. The oblique wing used on the AD-1 also had an airfoil shape which perfectly obeyed Bernoulli's principle of lift generation. However, one of the many challenges it encountered during the test flights is aeroelastic flexing and wing structure limitations. At higher sweep angles, generally above 45 degrees, the flexible fiberglass structure of the wing showed significant flexing and bending, or aeroelastic deformation. The wing lacked the stiffness needed to maintain shape and control, leading to poor handling. This was the result of the lightweight and low-cost fiberglass used in manufacturing the oblique wing. Pilots also faced complicated cross-coupling between pitch and roll. At full 60-degree sweep, even maintaining straight and level flight required continuous corrections in bank and yaw. Pitch, roll, and yaw are the three axes of rotation in flight. Pitch is nose up or nose down movement. Roll is tilting the aircraft left or right. And yaw is side to side movement of the aircraft. Beyond about 50 degrees of sweep, pilots reported oscillatory behavior. The aircraft became prone to unwanted rolling and was difficult to stabilize. This is because the test aircraft did not have advanced flight control systems. Without computerized or fly-by-wire controls, pilots had no automated assistance to counter the awkward cross-coupling and oscillations. There are several types of aircraft wing designs or wing configuration. Each design has its own unique advantages and challenges. Some aircraft have the ability to change their physical configuration during flight. They are called variable geometry aircraft. The oblique wing concept is similar to the variable sweep wing in operation. A variable sweep wing is also a distinctive aircraft design, where the left and right hand wings change their sweep together, usually backwards. The wings swing back for speed and forward for lift. This wing concept is mostly used in supersonic fighter jets. In a variable sweep wing aircraft, two pivot mechanisms move the wing forward or backwards. However, for an oblique wing aircraft, only one pivot mechanism is needed to sweep the wing. All of the two wing concepts have severe weight penalties, since the pivot mechanism must be robust and precise, but may be highly efficient in supersonic flights. To reduce drag, especially at high speeds, wings are often swept back. This design emerged with jet flight and remains standard. It delays drag as the aircraft approaches transonic speeds. Despite the handling challenges, the AD-1 fulfilled its main purpose. It demonstrated that an oblique wing could be flown safely and could pivot up to 60 degrees in flight. Though it achieved its technical goals, the AD-1 has raised more questions than it has solved. It paved the way for more capable future research that could fully test the oblique wing concept at transonic or supersonic speeds, with better materials and computerized control.